Hello, my name is Dave Winters, and this is my demo of my final project for UC Extension class EECS 497.2, Introduction to Digital Logic and Hardware Architecture for the winter 2012 quarter. What I have done is I have designed a binary calculator using the Atmel ATmega168 microcontroller, and I have breadboarded this here. On my breadboard, I have 4 groups of LEDs, one group for each operand. Operand 1 is in green, operand 2 will be in yellow, and the result LEDs are all in red with a low byte and a high byte. At the bottom of the board here, I have my 4x4 switch matrix. The switch matrix is scanned by port B, 4 lines for the rows, 4 lines for the columns. On the LEDs, I have the bit positions, bit 0 through bit 7, driven by port D of the 168, and each of the groups, operand 1, operand 2, result low, result high, are driven through 4 lines of port C. Each one of those lines activates one of these transistors, which syncs the common cathode LED group. Right now I'll go through a demo of the functionality to step through that. Right now at the bottom here I have my first function, which is clear. This will clear all the LEDs, so I'll just randomly punch in a result here so I can fill it all. Clear clears all displays. I can also clear individual entries. I have a separate 1 and 0 entry for each operand. I'll enter in combo as a 1 and 0s. I can clear operand 2 individually. I can clear operand 1 individually. And I also have a ones complement or not function, which operates only on the result registers. So right now, since there's all zeros in the results, if I do a ones complement, I will get F, 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 F there. And again, that will flip that back to zeros. And on the ones complement and the twos complement functions, what I've done is after those are executed, the original values are retained in the operand 1 and operand 2 displays. Now I'll go through and demo some of the math functions. First, a very simple one. We'll hit addition. Doing a 1 plus 1 gives us a 2. Clearing everything, let's do a 255 plus 255. Which gives us 1 FE. Right here you can see a 1 is up in the high byte of the result, and an FE is in the low byte of the result. Moving on to subtraction. Execute a 1 minus a 0. I get a 1. Flipping that around, doing a 0 minus a 1, we get a minus 1. And this is the one of the situations where the result will wind up being signed. Otherwise, all my results are unsigned, because I'm assuming unsigned inputs on all the inputs. So subtraction is the only situation where I should expect both signed and unsigned results. Moving on to a 240 minus a 255. So if I plug in 240 here, which is an F0, plug in 255 in operand 2, which is FF, execute the subtraction, I should get a minus 15. And in fact, we see we have all ones except for the 2, 4, and 8-bit positions. If I take the 2's complement of that, that should give me the positive version of that negative number, which is negative 15. And the 2's complement shows I get 15. And as I mentioned, once I do the 2's complement or the 1's complement, the original results are moved over and displayed in the operand displays. All right, let's move on to multiplication. Going to do a 2 multiplied by 4 and I should get an 8, and I do. We have a 1 in the 8 position. Moving on to 255 times 4. We will get 1020, which is 3FC in hex. So here we have a 3 in the high byte of the result and an FC in the low byte. Moving on to 255 times 255. And this is the max value we can enter using 2 8-bit operands. What we get is going to be FE01, which is 65,025, which, knowing that I'm using unsigned inputs, I should be getting unsigned outputs, so I know that this is a positive number, and it is 65025. Moving on to division, I'm going to do a 10 divided by 3. So plugging in 10 here in the operand 1, and a 3 in operand 2. So it's always operand 1 divided by operand 2. What I get is a result of 3, which is in the high byte, and a remainder of 1, which is displayed in the low byte. Now I'm going to do 10 divided by 11. And what I should get is a 0 with 10 as a remainder. And that's what I receive. Now I'm going to do 255 divided by 7. And what I will get is 36, which is 24 in hex in the high byte, with a remainder of 3, which is displayed in the low byte. And I've also taken care of divide by 0. So just to show that, I'll plug in 255 for operand 1, leave the 0 in for operand 2. And what I've done here is I test for it, and if that's what the operator is attempting to do, I clear operand 1 and show totally blank display. All right, moving on to the AND function, I'm going to just enter patterns in here to show logic functions. ANDing these two together should give me the same displayed result in the low byte. Again, these will result in only 8-bit outputs. Doing an OR of that will get me the same result. Doing an exclusive OR should get me all zeros because every bit is different, and that's what I receive. All right, one more example. I'm going to plug in a more interesting result. And if I AND this one together, I will get a 1 as a result. If I OR these together, I will get FF because I've covered every bit. If I exclusive OR them together, I get FE because bit 0 here has a 1 in both operands. Alright, and that is a demonstration of all the functions that this calculator performs. Thank you for watching.